Well, friends, it's my pleasure to welcome all of you to this institute and to this school. I do it on behalf of the director who could not be here, and also on behalf of the organizing committee. Some of the members of the organizing committee are here. Most of the arrangements for this have been done by Sivashis and Prabha and Hassan, and with the support from other organizing committee members, and I take much of the credit. We have tried to make this stay of yours as pleasant as possible. For some of you who have come long distance from the American continent and Europe, you may find it refreshingly warm. But I want to alert you that over the 2 weeks it can get much warmer. So we will do everything to make your stay here as comfortable and enjoyable, and the school as profitable as possible. But if you find any omission on our part, please bring it to the notice of one of the members of the institute participating here, and we'll try to see to what extent we can rectify. Andreas Mentor has been the mentor of this school. He has done all the academic organization, from conducting the speakers to deciding the content of the courses. It's entirely his job. I did not make any contribution. Unfortunately, he was supposed to come Saturday night. Unfortunately, he took ill. Now he has rescheduled to arrive here Tuesday night, Wednesday early morning. So partly I am standing in for Andreas as well. Otherwise, probably this inauguration would have been done by Andreas. So with this few words, I present to you Graeme Smith from India, who will be our first speaker, and he will give a course of 5 lectures on bosonic quantum computation. Graeme. Maybe let me add just, for those of you who are staying in Ginger, I want you to know that you can have breakfast here. You have an option. And I am saying this because I believe the breakfast at the institute will be found better by some of you or many of you.
Okay? I don't think the mic is on. Is it? Oh, okay. All right. Well, thank you very much. It's really exciting to be here with you. I want to thank Professor Simon and also Professor Sivashish and Hassan and Prabha. Sorry. And all of the organizers. Thank you very much for having me. I hope it'll be, I'm sure it'll be a fun school. Okay, so what I'm going to be talking about today, well, actually throughout the week, is the theory of bosonic quantum communications. So this is sort of a subset of information theory, which is kind of one of my favorite topics, and a topic that a lot of people will talk about this week. I'm just noticing that, would someone warn me when the time gets short? Okay. Thank you. Perfect. Thank you. So just as a show, well, okay, so what is information theory? It's this really nice sort of field that has a moment where we can identify exactly where it began. It started out with this paper in 1948 by Claude Shannon, and it's a nice topic that lies at the intersection of electrical engineering, mathematics, computer science, and physics. And in general, it concerns the reliable and efficient storage and transmission of information. So many of you, actually, I just wanted to take a show of hands. Has anyone taken who has taken a course in information theory? Okay, just classical, or quantum. Okay, some people have, so that's fine. All of you have used information theory, though. Who has a cell phone? Who has compressed data? Right? So information theory is really kind of crucial in a lot of the technologies we care about. Fewer of us care about Voyager, but it's quite interesting still that we can communicate with something that's left the solar system. And techniques like data compression or useful transmission with cell phones or modems, for example, all depend on developing reliable methods for transmitting information in the presence of noise. Okay, and quantum information theory is just recognizing the fact that we have this theory of information. We'd like to transmit data and pass it on and store it in reliable ways. And furthermore, the world is quantum. So if you want to get the true description of how information transmission and manipulation works in the world, then you've got to include quantum mechanics. And actually, when you do that, things get much, much easier. Not easier, more interesting. Much harder, actually. So the theory of quantum information theory includes such topics as secure communication, entanglement-enhanced communication, transmitting quantum information, and we still have these notions of capacity, error correction, compression, and entropy, these sorts of things. So I want to give you a little picture of the topics I want to cover this week. So today I'm going to give sort of a crash course on classical information theory and a little bit of quantum information. Okay? So we'll talk about the things, well, notions of capacity and error correction just in a classical setting and prove some achievability theorems. Tomorrow I'm going to talk about bosonic systems. Okay, so what's the correct way to describe bosonic systems and communication channels in a way that's going to be useful for us for doing quantum information theory? Okay, and this bosonic quantum systems, that's sort of code for, or you should always think in the back of your head of optical systems. We're going to be interested in a quantum description of optical systems for the purposes of communication. And at that point, we're going to move on to some more specialized topics, and to some extent, I'm not certain we'll cover all of these, but I'd like to. And if there are ones that look more interesting to you, please tell me at some point, and we can try to modify this as appropriate. So we can talk about classical transmission the transmission of classical information over quantum channels, and specifically bosonic quantum channels, and notions of additivity. I'd like to talk about that on Wednesday. On Thursday, I want to talk about transmitting quantum information and entanglement, as well as extracting noiseless entanglement from noisy quantum states. And then on Friday, I want to talk about quantum key distribution with continuous variables and notions of entropy power inequalities. And if I can, since we don't have any sort of precedent yet for this, I want to ask, please interrupt with some questions. Just I'm going to embed some errors at certain points. So if you spot the error that I've embedded, please let me know. And if we get to the end of the talk and you haven't spotted the error, I don't know. Okay, so information theory. I want to start with this example of flipping a biased coin. Okay, so let's say I take n coins, and they're independent and identically distributed, IID. this phrase is going to come up a lot. And the probability of the first coin being, or the probability of the coin being 0, which I'll call heads 0, is going to be 1 minus p, and the probability of it being 1 is p. Okay? IID, that just means they all have the same distribution. If I look at the ith coin, it's going to look like this. If I look at the jth coin, it's going to have these probabilities. And then if I look at the joint distribution of the two coins, it's just going to be the product of the two distributions. OK, so let's say I flip n coins. How many ones am I likely to get? P times n, right. And even better, if n is very large, I'm going to get around p times n ones. And if n is very large with very high probability, I'm going to get between like p minus delta times n and p plus delta times n ones. It's going to be exponentially unlikely that I get anything other than this as I let n grow. OK, so let's look a little bit more carefully at that. I mean, it's a simple example, but I think we can extract more information from it. So let's say I flip n IID coins, and they have the same distribution. Probability p, oh, I switched it. Probability p of being 0 and probability 1 minus p of being 1. With high probability, I told you if you swap those. So with high probability, I'm going to get p times n ones. And now we want to know how many different configurations there are. Well, that's pretty simple, too. It's just a combinatorial calculation. They're going to be n choose p times n, right? You just have to pick all the locations that are going to be ones and count how many such strings there are. Okay, and it's just going to be this simple formula, n factorial over p times n factorial, 1 minus p times n factorial. And then you use basically Stirling's approximation, and you'll find that the log of the total number of weight p times n strings is going to be approximately n times h of p. So what's this h of p? H of p now is just the entropy of this, the binary entropy of this probability of being 1 or 0. Okay? So it's minus p log p minus 1 minus p log 1 minus p. OK, so now, so far it's been sort of basic counting. But let's say I've done all these coin flips, and now what I want to do is transmit to somebody else what the outcome of all those coin flips was. Well, if I flipped n coins, naively you think maybe I'm going to have to send n bits to transmit that information to my friend. But if I know that I've flipped these n coins and they've come from this particular distribution, then I know with very high probability I'm going to end up with one of these typical strings of roughly p times n ones. And instead of transmitting the actual string that I get, what I'm going to do is just make a list, right, of all of these typical strings. And I'm just going to tell my friend, which typical string did I get? And with very small probability, I'm going to fail because I didn't get a typical string. But with very high probability, I'll be able to transmit all of these n bits by just telling which typical sequence that I've gotten. And I've managed to compress this information, instead of being n bits, down to n times the entropy of p bits. OK, so this is like data compression from Shannon's 1948 paper. And in a similar way, if I have some arbitrary distribution, not just a bunch of coins, but I have some probability, some random variable x, and some probability p of x of getting letter x, then if I want to transmit a bunch of coin flips with this, or a bunch of variables with this distribution, instead of transmitting, say, n times the log of the alphabet size of x, I can decide instead to transmit which typical sequence did I get, and I can compress down to this n times the entropy of x. OK, so what's the now let's say we're just talking about, I have some data, right? I have some random variables, x, and I'd like to compress them into the smallest possible size. So, does anyone, okay, so here's a question to you. Which is the most likely typical sequence? So let's say I have a sequence that a set of outcomes of my coin flips, and I know I have p times n ones and 1 minus p times n zeros. If I think about all such strings with that many ones and zeros, what do we know about the probability of those strings? Sorry. So, okay, let me put it this way. Which such string is most likely? Yeah, they're all equally likely, right? They all have roughly the same probability because they're just, the probability of getting something that's weight p times n is like, well, actually, I've written it here, okay? So if you think of it this way, if I look at the probability of a particular string, x1 up to xn, it's just given by the product of all of these probabilities. And remember, it's just, if this was just a bunch of zeros and ones, I would just have p to the number of ones times 1 minus p to the number of zeros, right? And that didn't care about which order these things happened in. It only cared about the weight of the thing. Okay, so they're all going to be equally likely. So how likely is that? Well, if I look at this probability of getting a particular string, x1 up to xn, I'm going to look at the log of it. One of the tricks in information theory is if you look at the log of things, typically what happens is if you have small differences, basically they go away, right? Because the rule of thumb is that the log of anything is like 3. Right? It's a joke. Okay? But it turns out that actually, if you're doing these estimates throughout, we're going to be doing a bunch of estimates of the size of things. And it turns out that because the quantities we're interested in, communication rates are measured in bits, and I start counting. When I do counting, I measure not bits, but something exponential in the size of the bits. I'm going to get to take a log, and when I take a log, if my estimate was off by a little bit, it doesn't really matter. If I have some additive error in the quantity I'm interested in, then that's going to translate into some essentially irrelevant error in the log of the thing I care about. Okay, so now let's look at the log of the probability of a particular particular bit string, x1 up to xn. Well, the log of it, because they're independent, is just equal to the sum of the logs of all of the individual letters. Okay, and let's think of it this way. This is actually a sum of a bunch of identical things. Right? These, if I pick x1, x2, x3, x4 all the way up to xn independently, then this is actually something like, well, this is just the sum of a bunch of things that I picked up. This is an empirical mean up to this 1 over n of all of the p of x's, right? So if I say minus 1 over n times log of this probability, it's going to be a great big average of all of these different instances of identical probabilities. Okay, so it's just going to be minus the average value of the log. Okay, and what's that going to be? Well, I can just compute what that is, and remember this formula for the entropy was just minus p of x times log p of x all summed over x. And that's exactly equal to minus the log of these probabilities. Okay, so this tells me that if I take a typical sequence, very likely I'm going to have the probability of that sequence be minus 1 over n times log of, or sorry, minus 1 over n times log of that probability is going to be something like the entropy of this random variable. So all of the typical sequences are going to have probabilities that are roughly the same, that are like 1 over 2 to the n times the entropy of the variable plus or minus some delta. Now, why do I have that plus or minus some delta? Well, the point is that if I...
Your Pn is not necessarily an integer.
Right. The Pn might not necessarily be an integer. And in fact, if I flip a bunch of coins, I'm not going to get exactly p times n ones. I'm going to get something very close to p times n ones. And the fluctuations are going to be, on the order of square root of n. But they're going to be a polynomial number in n of different weights that I get. And those different weights are going to lead to different probabilities here. And as a result, we're going to have different probabilities down here. But roughly speaking, they're close enough. Pardon?
Why does it come out to be a particular form, 1 by 2 to the power nx?
Oh, why does it come out to be like this? Oh, OK. So we look at this, and it looks at... Oh, okay, close to the... What should I do? Is that OK? OK. Sorry about that. OK, so you see right here, what I have is I'm imagining that I've taken n instances of this random variable x, and what I'm doing is summing up. Well, I know that log of the probability is equal to just the sum of the logs of those probabilities. OK, and then I'm using, if I write it like this, log of the probability, I get this. But now I'm going to move this minus sign in here. And now what this expression looks like is I have a bunch of identical, identically distributed and independent variables, which are now minus log of the probability of the ith x. Okay? And now I'm just taking an empirical mean of that. So then when n gets large, we know that with high probability, this is going to be within, let's see, within some small fraction of the mean of the variable. Right? This is, how do you, I guess this is law of large numbers. I think that's what it's called. You could show it with something called a Chernoff bound too. But the point is, if I take a large number of samples from a fixed distribution independently, the empirical mean, which is just the sum of all of the things that I get, all the outcomes that I get, approaches the actual mean of the single distribution in this manner. And like this, rather. And as a result, since this comes within plus or minus delta of the mean of this quantity, which is just the entropy, then when I exponentiate this thing, it becomes that. Does that answer your question? Is it? OK. Pardon? No, delta is going to be, well, actually, that delta is just going to be a constant, because I'm going to know that with exponentially high probability I get within there. But I could let delta be something like 1 over root n, right? And then I would still be OK.
This is the best from that
oh, no, this delta is the same. Okay, so the point of this is that we get more or less uniform distributions over typical sequences. All right. Oh, always base 2. Until tomorrow. I'm sorry, okay. Because actually, usually you're doing information theory, you do log base 2 because you're interested in bits. But then when you're doing information theory with continuous variables, if you try to do it in bits instead of nats, then you always end up writing natural log of 2 all the time. So tomorrow we'll use natural logs. Today we'll use base 2. Anything else? Okay, so this kind of, so far we covered like notions of data compression, right? I give you some information, and it's drawn from some distribution that you know about. You want to compress it to a minimum amount. I didn't prove it. Maybe we can discuss it in tutorials. But this is as good as it gets. You can compress down to the entropy. Sorry, you can compress down to the entropy by this typical sequences stuff, just labeling which typical sequence your data is, and you can't push it any further. Okay, so at this point, I want to talk now about a way of measuring correlations between different random variables. Okay, so in some sense, this entropy measures the amount of information in a variable, and maybe I should just say this to make sure it was clear. I'm sorry to do this to you guys. We can turn on the light again. Thanks. It's just that let's say I have something like 2 to the n times entropy of p typical sequences. I say that that's n times entropy of p bits because if I have k bits, there are 2 to the k different messages I can send. Right, so if I have 2 to the n times entropy typical sequences, I get to take a log in order to say how many bits it takes to transmit. And furthermore, I talk about the compression rate or the information rate of this as just being the number of bits divided by the number of variables. So that's why we end up talking about the entropy of the distribution as being the amount of information contained in that random variable. Okay, so now we've been talking mostly about just a single random variable, but what if you have 2 random variables and they're correlated in some way? Okay, so let's think about this. Let's say you and I, we share 2 random variables. You have y, and I have x. And I want to transmit x to you. If you didn't have y, we've already discussed how much information I have to transmit to you if I want to get x over to you. And when I say I have x, what I really mean is I have a bunch of independent copies of x, and I'd like to transmit all of those copies to you. In order to do that, I just have to pick out which typical sequence I want to transmit to, which typical sequence I've got, and I tell you which one of those it is, and I can manage to transmit all my x's over to you with just at a communication rate of just the entropy of x. So now, let's say you have some random variable y, and it's correlated with x. Well, that should help you in some way, right? For instance, if it's just a copy of x, then I don't have to transmit anything at all. That's perfect. You've already got x. My job is done. But if it's only correlated with x, or it's some noisy version of x, and I want to transmit x to you, what are we going to do? Well, oh, I put my pointer over there. Well, what we're going to do is, let's say, okay, sorry. So I take my random variable x, and I feed it into some noisy channel, and you get y out. We want to know how much x or y tells us about x. Well, after you get y, we need to figure out how much more I need to tell you in order for you to figure out what x is. So, well, let's say you get y. You can kind of figure out what the new probability. You have to update your estimate of the probability of x. So instead of me having a string of random variables x, and you have no information, you have some extra information, y, about it. So you have to update and figure out what the conditional probabilities of x are given the values of y that you've got. Okay, so you can do that using this what is it, Bayes rule. And then, well, the nice thing is, remember, the entropy of a random variable tells you how much information I need to transmit to you in order for you to figure out what that variable is. And in this case, we have a new set of distributions, these conditional distributions on y. And if I fix y, for example, we can figure out what's the entropy of the residual probability distribution. So this conditional probability distribution averaged over all different values of y. Right? So just like we saw on the previous slide, what we need to do is take the average of minus the log. Instead of just the probabilities, we have to take minus the average of the log of the conditional probability that you compute once you figure out what y is. And that tells you how many bits per random variable you're going to need to transmit. And then we call this quantity the conditional entropy of x given y, and we can calculate what it is. It's just given by the average of this minus log of px over py, or pxy over py, where this average is taken over all values of px and py. And in fact, it ends up being equal to this difference of the joint entropy of x and y and the entropy of y. So that's how much information, if you're holding on to y, and I want to transmit x to you, this conditional entropy is how much information, or how many bits per bits per instance of the variable that we have, I'm going to have to transmit to you. Okay, and the savings that you get for having y is just the difference between x, the amount of information I would have to transmit to you if you didn't have y, and the amount of information that I have to transmit to you when you do have y. It's given by this difference of h of x and h of x given y, which satisfies this nice formula. And we call this the mutual information. So this mutual information is just some way of measuring the correlation between two random variables in this operational way, in the sense that operational in the sense that it tells me how much savings do I get when I try to transmit x to you when you have y as opposed to when you don't have y. Okay, so is this idea here clear? Okay, so we got close to the idea of noisy transmission. This is instead some sort of data compression, right? If you have some partial information, and oh, maybe I'll use an example here. So let's think of x and y as these two correlated things, right? So let's say I don't know, x. Yeah, I'll use an example. Let's say x is the front page of the Times of India, and y is the front page of the New York Times, right? If I have the front page of the New York Times, and you want to tell me what happened on the front page of the Times of India, there's extra information there. You're going to have to tell me more information. But it actually helps if I have the front page of the New York Times sitting in front of me. You could just say, oh, Graeme, was there a story about, I don't know, what was on? I didn't see the New York Times this morning. Well, probably, for example, the New York Times and India, they both have discussions of like international affairs. On the other hand, there's going to be all this little bits of extra information that you have to send to me about things that happened in New Delhi, right? And similarly, you probably are not going to have, if you're holding on to the Times of India front page, and I'm looking at the front page of the New York Times, I'm going to have to look at this and say, well, now I have to tell you about the mayor's race in New York, and I have to tell you about this other stuff, but there's all this other extra information that you've already got. So the basic idea is, if you have some if we have some correlated information, I just have to tell you all the bits that you don't know yet. And we can measure how much those bits are in terms of this mutual information. Okay, so that's closely related to the next topic, which is noisy channel coding. So now I want to take some time to discuss channel capacity. So let's talk about a noisy channel. What do I mean by that? Basically, I just mean I have some device that I'm going to try to use to communicate to you. Maybe, if it helps, think of it as a piece of optical fiber. And I have some signal variable that I can put into it, like maybe the intensity of a laser. Maybe it's my wireless card. Right, and I have some sort of input signal to the channel here. And then when I try to do a transmission, there's going to be some corruption of the signal that I send. And at the receiver, there's some output here. Okay? And there's some noisy input-output relation between the input and the output. And we want to make use of that in some way to transmit information noiselessly, right? Okay? And this was sort of the thing people didn't really realize you could do back in 1948, but sort of magically you can do it. This is the amazing thing. You have all of these sort of faulty devices here. You know, there's just some conditional probability distribution of getting a signal Y given that you have output X. And nevertheless, if you have a bunch of independent copies of this noisy channel, so you might have, you might think, if you're thinking of optical fiber, think of this as the use of, you know, to think of these as time binned. So this is the signal I send in one time. At some later time, I send another signal all the way down. And it turns out that you can actually reliably transmit information perfectly from one side, or from sender to receiver, even though all of your transmission or all of your channels are actually faulty. Okay, so the rate at which you can do this is called the capacity of the channel. So this is just the definition of the capacity of a channel. So given n uses of a noisy channel, so we have n independent uses of a noisy channel characterized by some transmission probabilities. You want to take some message m, and you want to encode it into all of the inputs of the noisy channel here in such a way that a receiver who has access to all of the outputs of the noisy channel here can do some decoding operation in order to recover some estimate of your message. We'll call it m prime. And we're happy if, with high probability over all of these random jostlings that happen in the channel, that this estimate of the message is actually equal to the intended message, m. Okay. Now, I mean, one thing you could do is just repeatedly, you know, let's say this is just has a bit in, and there's some chance of the bit being flipped. You can repeatedly just transmit your bit over and over again, and chances are eventually, well, you know, eventually if you just do some sort of majority vote or something, you're going to do a good job. You're going to get the right answer. But the problem is that that's extremely inefficient. You get to send only one bit, and you have to use your channel many times. It turns out that you can do better than that. You can do some more complicated encoding strategies, and then you can actually transmit at positive rate, meaning that the total number of messages you can transmit, well, the total number of bits you can transmit, which is log of the total number of messages, per channel use. So the number of bits per channel use that you can transmit actually will approach some constant that's independent of this the number of channel uses you have. Right. So in the asymptotic limit, we're going to be able to transmit some fixed fraction of bits from sender to receiver per channel use. Okay. And the capacity of the channel is just defined as the maximum number of bits you can transmit per channel use in the limit of many channel uses, with the probability of error decreasing as the number of channel uses grows. Okay, so now I want to talk about the particular example, the binary symmetric channel. So this is just okay. The binary symmetric channel, it works like this. It has two input signals. You can choose to put in a 0, or you can choose to put in a 1. And then with probability p, your bit gets flipped. So the probability p, if I put in a 0, I get a 1. With probability p, if I put in a 1, I got a 0. And with probability 1 minus p, I get the right answer. Okay, I'm going to do a pop quiz. Let's say p is a half. Does anyone know what the capacity of the channel is? 0. Good. Why? Because if p is a half, there's no correlation between the input and the output, and you're not going to transmit any information with that. That's sort of, I mean, if you set p equal to a half and there's no correlation between the input and the output, obviously this is not going to be useful for transmitting information. The more remarkable thing is, if p is not equal to a half, any other value of p, then this thing is useful for transmitting information, and at good rates too. Okay, so these are just the conditional probability distributions of this channel, and we're going to try to figure out what the capacity of this channel is. So remember, we have many uses of the channel. So we're going to have many input strings, n, let's say, and we'll call the input string x, x1, or x to the n. So usually, this x to the n just means that you have an n-bit string, and the first value of this bit string is x sub 1 all the way up to x sub n. So what happens when I try to put this into many uses of my noisy channel? Well, if you remember this coin flipping example that we had, right? These bit strings, each of the individual bit strings are going to get flipped with some probability p. And then remember, when you flip a bunch of coins with some probability of being 1, that is p, the total number of ones you tend to get is like 2 to the n times, is p times n. And furthermore, there's something like 2 to the n times the entropy of p typical ones that you'll get. So if I put in a particular bit string, x to the n, I'm going to, and then I feed them into this binary symmetric channel with crossover probability p. Then I'm going to get that one bit string will typically get mapped to one of these 2 to the n times entropy of p typical errors, typical target strings. Okay, and that's out of a total number of 2 to the n possible outputs. It looks. All input strings. Right. So then all input strings are going to get blown up to this size of 2 to the n entropy of p. And if I want them to be reliably decodable, they can't overlap, right? This spray has to be different for each of the different messages. So, well, if I have another bit string, I'll be lucky if it doesn't overlap. And I have to organize my input bit strings that are trying to transmit different messages in such a way that the image of these things under the action of the channel doesn't overlap much. Or actually, to first order, let's say it just doesn't overlap. Okay, and if I want to make sure that's going to happen, I can't take too many bit strings because there are 2 to the n times entropy of these guys, these typical strings here, and well, how many such bit strings could I possibly have? I don't want to fill. I want to just fill up the total number of output bits, right? So the total number of input strings that I could possibly deal with is well, look, each thing gets mapped to 2 to the n times entropy of p, different strings, and I want to make sure that they don't overlap. So if I'm going to have capital M messages that I transmit reliably, capital M is the total number of these different sort of sets that I'm trying to make sure don't overlap, times the size of the set better be less than the total number of strings in the output. So this tells me that no matter what my coding strategy is going to be, I better make sure that m times 2 to the n entropy of p is less than 2 to the n. And that just transmits to 1 over n times log of the number of bits, or sorry, log of the number of messages I send. Is this in the way? Better be less than 1 minus binary entropy of p, this entropy function. So that gives us an upper bound on the capacity of this channel. But it seems like a pretty, well, it turns out actually that this upper bound we can achieve. And that's kind of remarkable, right? There's some way to pick all of these different input strings so that if I want, well, basically so that I can engineer when typical errors get applied to each of those input strings, the spray that I get with all of these typical errors tends to make sure that all these different sets don't overlap. Okay, and what I want to talk about now, oh good. What I want to talk about now is how do we show that? I mean, if I gave you a list of typical errors, or I gave you a list of errors that you wanted to correct for, and asked you to design error correcting codes for that, actually it's quite a difficult problem. It's combinatorially challenging, and it's a lot of fun, but it's totally not trivial to construct good error correcting codes for this kind of channel. Actually, so the capacity of this channel, it turns out, this binary symmetric channel, is just this 1 minus entropy of p. And that was shown in 1948. Probably the first construction, well, basically by the late 90s, we had reasonable constructions of codes that can actually achieve this. So what happened in between? How is it that we could know that the capacity is this thing, this amount, but we didn't know how to construct codes? Well, there's some non-constructive proof that such a code exists. So what I want to tell you about now is how do we prove there are good codes for this binary symmetric channel? So basically what you do is you say, look, I have a target. I know how big I want or how many messages I think I can transmit. I'm going to try to transmit 2 times this n times I want this m to be equal to 2 to the n times 1 minus entropy of p. And well, what strategy am I going to use to select these code words? Basically, I'm just going to select a bunch of random code words. I'm going to select a total number of code words equal to this capital M. I'm going to choose them all randomly. And the strategy is going to be to show that with reasonable probability, this choice, or at least with non-zero probability, this choice leads to a code that has all of the properties that we want. Okay, so what are we going to do? So I'm going to choose let's say I'm going to fix R. It's going to turn out that when R is equal to this quantity or less, that this construction is going to succeed. And here's the strategy. I choose 2 to the n times R code words randomly, just 50-50 random bit strings. N is going to be large. And what's this x sub n super n? Well, remember each message is going to be a bit string of length n. So n tells me that it's a length n bit string, and m is just the index that labels which code word I've got. Okay? So I'm going to choose these guys all at random, and then here's the decoding strategy we're going to look at. So I put this x sub m into the channel, and then it's going to get totally distorted by all of these errors. There are going to be 2 to the n times the entropy of p different errors. And at the decoder, what I'm going to do is I'm going to say, well, let me see if by flipping any 2 to the n times entropy of p bits, I can get back to some code word from the code book. If there's exactly one code word that's consistent with this with some typical error corrupting it, then I'll report that as the message. And otherwise, I'll report an error. If there's no code word, I'll say error. If there are two code words, I'll also say error. Okay? And the point is, we have to show that. Well, we already know actually that this decoding sphere is big enough that with high probability the correct error is in there, right? We know the correct code word, right? I take the code word x sub n, and then I put it through the channel. Then with very high probability, we agreed that the error strings, so the string that tells you whether or not each particular channel use got a bit flipped, is going to have this weight, is going to have some weight that's close to this. Okay, so we know that when I look at all of the strings that are within sorry. When I look at all of the strings that are within this number of bit flips of the message that I get, with very high probability, I'm going to find at least one message in there, and it's going to be the correct one. So now I just have to worry about, when I do this selection of code words randomly, what are the chances of there being two code words somewhere in the same in the same sphere of all of these outputs? So what are the chances of that? Okay, so here's another picture. By the way, when you're dealing with channel capacities, there are sort of two different kinds of arguments you have to do usually. You have to do something called a direct argument, which is the coding theorem. That means, you have some quantity you're trying to show as the capacity of your channel. You need to show two things. You need to show there exist communication strategies that achieve this rate, and that's called the direct part. That's called the direct coding theorem. And then you need to show that any strategy, no strategy can actually exceed this rate. And that's called the converse, usually. And as a rule, the direct coding part is done by some sort of random coding argument, and the converse involves some sort of entropy inequalities. Okay, so actually, I think in the tutorial section today, we're going to talk a little more about entropy inequalities. So what I want to show you now is just a sketch of the achievability of this 1 minus entropy of P for the binary symmetric channel. Okay, so remember the strategy. We're going to choose a random code word, and then the channel is going to act. So, for example, this guy got mapped to this red one. And then I'm sitting here at the receiver. I just get this red bit. I don't know that the correct message was actually this guy here. There are something like 2 to the n times entropy of P different bit strings that are consistent with the message that I just got. You want y is
that red dot.
y will be this red dot, but
That will be basically
to the
because you estimated it to be white there.
yeah, this is definitely what.
Or y should be 2 to the x.
That part I don't understand. Y should be 2 to the.
Well, it's an estimate of y.
It's an estimate of y. It's an estimate of the total number of different y's that you can get, or that's definitely right. But if I'm trying to transmit something to you, you have some string, and you have to guess now what the input was.
Yeah, given the input, don't I conclude that y is my output?
Yes, definitely. But that's not how channel coding is going to work, right? I'm transmitting to you. I have some message I'm trying to send. There's some noisy medium between us, and you get some corrupted version of my message. And then you have to guess my message. So you know exactly what y is, but now you have to figure out, was this the message, or was that the message, or was that the message? And they're all equally consistent, right? because they're all within the correct typical weight of the thing that you received. Okay, so what we have to worry about is, for this particular y, we need to know, well, we know that there's going to be a correct code word in there, because the strings are going to be typical, but we need to know what are the chances that when I chose another random code word, say over here, that when I enlarged that by this factor, I also ended up overlapping with this sphere. So I'll choose one more code word, and the chance that that code word is going to be in the sphere is actually easy to calculate, because we know the size of the sphere. We know how many different bit strings are in here. It's just 2 to the n entropy of p. If I choose a random code word that it's going to be within that decoding sphere, is just the volume of the sphere divided by the volume of the whole space. So it's 2 to the n entropy of p divided by 2 to the n. Okay. So that's just when I add one more code word. Now we have to figure out how many code words can I add before I start to believe that it's likely one of them is going to fall inside there. Well, if I add 2 to the n times r code words, then the chance that one of them lies within this circle here is just 2 to the n times p over 2 to the n, right? That's the chance that one of them lies in there, times the number of extra code words I add, times this 2 to the n times r. So the total chance that one of the code words falls in this particular circle and makes my decoding strategy fail is just the product of those things is going to be 2 to the n times entropy of p plus r divided by 2 to the n. Okay, so now as long as I pick this r to be strictly less than 1 minus entropy of p, I'm leaving out some of the little epsilon delta stuff, so it's actually strictly less than 1 minus p minus this delta here. Then this chance that for that particular random code word, there was some other code word in my code book lying within the decoding sphere, actually goes to 0 and it goes to infinity. Okay? So this tells me if I randomly choose p, or choose a set of code words of size 2 to the n times r, then the probability for a particular code word that there will be some other code word lying within weight n times entropy of p of that original code word is going to go to 0 as n goes to infinity. So that tells us that the average probability of decoding error, averaged over the code book, and averaged also over choice of code book, is going to be small. Okay? And since I'm choosing random codes of this particular size, and I say what's the average error probability for the random code that I've selected, since the average value of the error probability is low, there has to exist some particular error correcting code that has a low value too, right? If you have a random variable and it has a low average, there are instances of the random variable that are also low. Now I want to emphasize something here that we're talking about average error probability. So what does that mean? That just means that if I average over all messages in my code book, the probability of an error for message m, this thing is going to be less than, or I can make this less than or equal to some epsilon for all epsilon. Now, you might want to do better than that, right? You might like to say, well, I have this code book. Rather than having an average error probability that's less than epsilon, I want to make sure I can have a worst case error probability, or worst case error probability that's less than epsilon. In other words, I might want to make the probability of error given message m be less than epsilon for every m in my code book. And it turns out I can do that too. So why is that? Well, what we already showed was that there's a code with radar where R is anything less than this 1 minus entropy of P, so that the sum over all entries in the or all code words of the probability of error given that code word, P sub I, that sum averaged over, well, sorry, that average over code words is less than epsilon. So now what I want to do is take this code that we showed exists by random coding, and I want to extract some fairly large subcode of that original code. And I want to do it in such a way that that subcode that we select actually has good worst case decoding error rather than good average decoding error. So what am I going to do? I'm going to let this n sub 2 epsilon just be the total number of code words in my code book that have conditional probability of error bigger than 2 epsilon. Okay, epsilon is the decoding error, the average decoding error rate. We showed that that's going to go to 0 as the length of the code grows. Now I want to take the subset of this code, this code that we designed, and pick out the code words that have slightly high conditional probability of error. Okay, so epsilon is going to be small, so 2 epsilon is still going to be pretty small, but these are sort of the bad guys in the code. So now I want to estimate the number of code words that have this sort of slightly elevated conditional error probability. Well, it's actually not hard to do that. So, so I'm really sorry. My body thinks it's midnight. Okay. All right. Good. So, what is the total number of slightly bad code words? Well, let's figure it out. Right here we have 2 epsilon times the number of code words with error probability bigger than epsilon. Well, and I divided by 2 to the n times r. So over here I've got 1 over 2 to the n times r. Fine. And now I know that this n2 epsilon times 2 epsilon is going to be less than or equal to the sum over all of the error probabilities of just these n2 epsilon terms, right? So now I've taken all of the bad probabilities of error here, bigger than 2 epsilon, and I'm just going to sum over all of them, but only for the code words that are strictly bigger than 2 epsilon, right? So each of these p sub i's is bigger than 2 epsilon, so I know that this sum is bigger than the total number of terms in the sum times 2 epsilon. But I know that this restricted sum is actually strictly less than the unrestricted sum, where I sum over all code words. Okay? And I know because of the properties of this code, because it has a good error probability, that that's less than epsilon. Okay, so that means that the total number of code words in my code is less than 2 to the n r, that's the minus 1. Okay, so what's that? That means that less than half of the code words actually have this bad error probability. Okay? I'm just going to throw them all away. Okay, it might sound bad. I took an error correcting code that seemed to be working okay. I throw away half of the code words. But actually, that's not such a big deal, because what we're interested in is showing that we can achieve this rate. And the effect on the rate of throwing away half of the code words is actually not too bad, because remember, we have this formula that we take log of the number of messages divided by the total number of channel uses, and that tells us what the rate is. if I divide this in half, I only change the rate by 1 over n. And we're interested in scenarios where n is getting large. So actually, this doesn't affect the rate very much, but it gives us a much better property of the code, because now instead of working on average, the code works in the worst case. And this is actually sort of a very typical kind of argument that we find in information theory. We have some task we want to accomplish. Through one manner or another, you get some guess for what the best rate you can achieve for this task is, and then you can show by random coding strategy that actually there exists some code that approaches this rate. Okay, and all of this we can actually do very similar argument for the general case of a noisy quantum channel. Now, instead of just binary strings, instead of just choosing random bits and having binary strings, we have some input distribution x, and we are going to have to vary over this input distribution. Earlier, we just used a totally uniform distribution on x, but for some channels, you may want to use different distribution for your code book. But you take a fixed distribution that generates via the channel a joint probability distribution on x and y. And what you want to show, what the capacity of the channel is in this case, is just the mutual information that we saw before of this of these two random variables x and y, and you have to optimize over all random variables x. And the structure of the argument is the same. They're going to be 2 to the n times entropy of x, typical x's. For typical y, they're going to be 2 to the n times conditional entropy of x given y candidate messages in a decoding sphere. And if there's a unique candidate, you report it. If there's not, you fail. And each sphere contains a fraction, this fraction of the outputs. So we have to figure out the size of the code that we can pick before we start getting overlapping spheres. So the size of the code is just, basically find m that you can multiply by this to keep it less than 1. And that tells you the total number of code words you can pick. And in that case, it ends up being, you can pick a rate r. You can pick 2 to the n times r code words with r strictly less than this mutual information. And then you do this same trick of throwing away half the code words to ensure that you have worst case error probabilities that go to 0 rather than average case error probabilities. Okay, so now we've showed that for any we showed for the binary symmetric channel in detail, and I told you for a general channel that for any input distribution p of x, given these probabilities, these conditional probabilities that characterize the behavior of the channel, these p of y's given x, we can approach the rate given by this mutual information. And by picking the best probability distribution, we can achieve this maximum mutual information between x and y. And this is the direct part. Then you have to prove that you can't do better if you want to figure out what the capacity of the channel is. And proving there's no way to beat this mutual information bound is actually, it's called the converse. So we're gonna think about converses. There's some inequalities about entropy that I will discuss in the tutorials, but I'll just tell you they're kind of nice. If I have a joint entropy of 2 random variables, x and y, that's no bigger than the sum of the individual entropies. It's called subadditivity. And here's a slightly more complicated inequality that I like. It's more or less equivalent to strong subadditivity, and we'll use it in some later parts of the discussions. It just tells me if I have 2 random variables y1 and y2, and 2 random variables x1 and x2, the conditional entropy of y1 and y2 given x1 and x2 is no bigger than the sum of the individual conditional entropies between the 1s and the 2s. So this is a special case of that, but this is, I think, much nicer. So we'll use just the first one to prove that no good code can actually transmit at a rate better than maximum mutual information between x and y. Okay, so how is this going to work? Well, first we have some code, and there are 2 to the n times r strings of n letters, right? And we just let this bold x to the n be a uniform distribution on the code words, so that you get the ith code word with probability 1 over 2 to the n r. And now, because the channels, I'm going to stand over here because this is a long slide. Because the channels are all independent, the probability of getting y1 up to yn, given all of the inputs, x1 up to xn, is just equal to the product of all of these conditional probabilities. Okay. And let's go through this line by line. So we want to look at this conditional entropy of yn given xn. It's just going to be equal to, remember this definition of conditional entropy, it's equal to the average of minus the log of these conditional entropies here. And in this case, because these guys are all independent, those guys, when we take minus the log of this guy, it's equal to the average of minus the log of those guys, so it's equal to the sum of all the averages of minus log p of yi given xi. And because this is a large average, that ends up being equal to just the sum over all code words I of the conditional entropy of y, the ith bit of code word, or of the received message, given the ith bit of the transmitted message. Okay? So the conditional entropy of the entire received message, given the entire code word, is just equal to the sum of the conditional entropies of the individual bits of the received messages, given the individual bits of the transmitted messages. That's just because all of the noise is independent. So now we want to look at the mutual information between y to the n and x to the n. Right? This, remember, is the received code word. This is the transmitted code word. And the reason I'm talking, these are in bold, is because this is the random variable rather than the specific instance. Okay? So now this formula we had for mutual information tells us that this difference in mutual informations is just equal to the entropy of this y to the n minus this conditional entropy. And the subadditivity property I mentioned earlier tells us that this first term is no bigger than the sum of the individual entropies of those y's. And this argument that I showed you above tells us that this second term is just equal to the sum of these conditional entropies between these y's. Okay? So this is a sum now over all I of the mutual information between y sub I and x sub I, where these are just the ith bits of this random variable x and the ith bit of the output variable y. And now these are specific distributions of x and y that you can generate by picking some distribution. Sorry, these are specific distributions on the input. So the mutual information in each case for y sub I and x sub I is going to be no bigger than the maximum value I can pick over all distributions x. So this sum is going to be upper bounded by this n times maximum mutual information between x and y. Okay, so what this shows is the mutual information between the message. This is the code word, the sort of uniformly chosen code word, x to the n. The mutual information between that and the output of the channel is going to be no bigger than n times the maximum mutual information between the input and the output of the channel. Okay, so now what does this tell us? Remember, we chose this code book so that these x to the n's were going to be uniformly distributed over my 2 to the n times r code words. When I have a uniform distribution over a bunch of different code words, the total entropy of that uniform distribution is just log the number of code words. So as a result, this mutual information is just equal to n times the rate of the code minus this conditional entropy of x to the n given y to the n. Okay? So now we know that this is no bigger than this mutual information times n. Finally, we need to show that this conditional entropy of x given y is low. However, I told you this was a good code word, right? And no, a good code book, right? And that means if I take the output of the channel, I can figure out with very high probability what the input of the channel is. That means the conditional distribution over code words, given the output of the channel, is highly peaked. Basically, with very high probability, there's the correct code word, and with very low probability, there's a bunch of other code words. And that kind of distribution has very low conditional entropy. It actually is going to approach 0 as this n grows. And that means this inequality here is just going to become n times the rate of the code is no bigger than n times the maximum mutual information of the code. This is the converse that we wanted to show. Okay, so this is a sort of a recap of the crash course on classical information theory. So the point is that information theory is about efficient and reliable transmission of storage of data. And I focused on the problem of communicating in the presence of noise, and specifically how to figure out how to randomly choose good error correcting codes. The capacity, it's just the maximum rate of communication for a noisy channel, and it's given by this mutual information, the best mutual information that you can generate between input and output distribution of your channel. Mutual information is just this thing that tells you the right way for information theoretic purposes to measure the correlation between two random variables.
Right, maximum over x will mean maximum over p of x.
That's right, yeah. Sorry, yeah, right. That's right. You maximize over the input distribution. And this capacity proof involved two parts. There was this direct part where we showed by a randomized argument that there exist good code words with low probability, good codes with low probability of error. And the hard part of that, in general, is doing the error estimates, figuring out what's the probability of error for your randomly chosen code. And the second part is the converse, showing that there are no codes that can do better than this achievable rate. And the strategy there is you use entropy inequalities. Okay, so now I want to say, I think I have 10 minutes. I want to say a few things about quantum information theory and notions of quantum capacities for quantum channels. Okay, so I want to talk a little bit about quantum states and channels, and then just definitions of capacities. Okay, so you remember a classical channel was just some method, some rule for taking input signals and mapping them to output signals. It was parameterized by some conditional probability distributions. The capacity was just the total number of bits per channel use I could transmit in the limit of many channels. And it was given by this maximum mutual information between x and y. Quantum states are not, well, basically, classical probability isn't rich enough, and classical information theory isn't rich enough to describe quantum states, so we need to develop information theory involving these quantum states. So as you know, quantum states, they're just, pure quantum states are just complex unit vectors. And mixed quantum states are just trace one positive semi-definite matrices that correspond to probabilistic mixtures of these unit vectors. And you can always think of one of these mixed states, and I always do, as just being a bipartite pure state with a partial trace applied to it. So if I have some rho sub b, I can always think of it as just, I started with some pure psi sub ab, and it's and then traced out a. So there's a whole story about entropy in typical spaces also with quantum information. And just like we had this game with typical sequences initially, we talked about how do I transmit this string of random variables drawn from this distribution on X. You can say, look, let's say I have some density matrix rho sub B. It's purified by psi on AB. Then for rho B, I can also define an entropy. It's just this von Neumann entropy minus trace rho B log rho B. It measures the amount of uncertainty in B, just like the entropy of X measured the amount of uncertainty in X. And it actually performs the same function of the entropy of this random variable X, but for this quantum state. Okay, so what do I mean by that? Just like if I have an X and I wanted to transmit it to you, and we wanted to know how many bits I needed to transmit, if I have n copies of some state psi sub AB, and I want to transmit B over to you and maintain the correlations with this A system that I'm not allowed to touch, then there's a way I can reversibly map B to a space of dimension 2 to the n times the entropy of B. I can compress my states on B down to that and pass them to you. So now I only need to send 2 to the n times entropy of B different quantum states, which means total number of qubits that I need to transmit is just n times entropy of B. And this is exactly the typical space of your quantum state. And these are these are basically identical to the notion of typical sets for information theory, these 2 to the n times entropy of P strings. You just diagonalize rho B. That gives you some probability distribution on the eigenvectors. And then this space is just spanned by, you take all of the eigenvectors associated with typical strings of eigenvalues, and you can map this down, this state rho B down to that. So von Neumann entropy has lots of nice properties that will be useful. So this is the definition. So one thing we know is that the entropy of some state rho is strictly positive, or it's positive, and it's 0 exactly when the state is pure. Another thing we know is if it's a d-dimensional space, this entropy of rho is no bigger than log d. And it satisfies a kind of concavity property that we're going to use, so that we'll use later. Basically, if I take a mixture of one density matrix and another density matrix, then the entropy of that density matrix is bigger than the average entropy of the individual density matrices. By mixing things together, I make them more uncertain, basically. And it satisfies a continuity property. Just that's something we sort of implicitly used when we were talking about the converse. This is remember we talked about, well, almost certainly the receiver knows what the input message was. That means the conditional probability is 0. That means the conditional entropy is 0. We were sort of implicitly using this kind of argument about, or this kind of inequality for the classical entropy. Okay, and it also satisfies this subadditivity notion, this subadditivity property. The entropy of AB, a joint system, is no greater than the average or the sum of the entropies of A and B. And furthermore, it satisfies an additional property, the strong subadditivity, which is very nice, and I think probably we'll talk about it later. But the point is, classically, actually, it's very easy to derive this quantity, this inequality from that inequality, but quantumly, this is actually much more complicated. Okay, so now, noisy quantum channels, instead of having this conditional probability distribution from some input signals X to some output signals Y, for a noisy quantum channel, you have some evolution from density matrices to density matrices. So a noiseless evolution is very simple. It's just a unitary. Rho gets mapped to U rho U dagger, where it's this U is, well, it's a unitary. And a noisy quantum evolution, you can always think of, it's a mapping from some rho to rho prime, but I can always think of it as as some reversible interaction with an inaccessible environment. So in comes some pure state ancilla. It interacts noiselessly with the environment, and then the environment gets traced out. I can always think of this n rho as this kind of mapping. And that turns out to be very useful when you're trying to do information theory with noisy quantum channels. OK, so we talked about states and channels. Now I want to tell you just the definitions about quantum capacities and some statements of coding theorems. We're not going to prove those coding theorems. I think you will prove some of those coding theorems later in the week with either Andreas Winter or Pranab Sen. But for now, I'm just going to state some definitions. So the classical capacity of a quantum channel, what's that? Well, I'm trying to transmit classical information like I do, like in the earlier part of the lecture. We have some classical random variable. We want to transmit it. So I make some code book. There are some capital M code words. But the code words now are no longer bit strings. They're quantum states that I'm going to put into my noisy quantum channel. And there's a quantity, and I'll be happy, right, if I put one of these states into the channel. I let the channel act on all of these states, and then the receiver gets some quantum state out again, and then does some decoding operation to guess the message. If the receiver can guess the message with high probability, we'll say it's a good code. The rate of the thing is just the number of bits transmitted per channel use. And it turns out there's this thing called the hole-in-hole information that looks a lot like the mutual information. You now maximize over input ensembles. So I have some random probability, some random variable x. And based on x, I choose some density matrix rho sub x. And then I evaluate this mutual information quantity, mutual information between the random variable x and the output of the channel that I get by preparing this rho sub x and then acting on that rho sub x with the channel. So I make this density matrix, and I just evaluate the mutual information naively using this formula, the difference between the individual mutual informations and the joint mutual information. That's called the hole-in-hole information. It turns out that you can show via random coding arguments that this is an achievable rate. And furthermore, you can show that if I evaluate this achievable rate on many uses of the channel and take this limit as n goes to infinity, then the classical capacity satisfies this thing. It turns out, in this case, for the quantum case, we can't simplify this down to just being a single use of the channel. This single use of the channel, we have to do this what's called a regularization. On Wednesday, I'll talk more about this notion of regularization and how it's different from the classical case. I'll just say maybe 3 more minutes. Is it OK? OK, good. OK, so another thing you might be interested in doing is transmitting classical information from sender to receiver, but doing it in such a way that an adversary who has access to all the environments of the channel isn't able to learn anything about the messages sent. So that's just this is related to quantum key distribution, and the basic idea is you want to have all of the information you try to send to go from here to there, and no information be leaked from here to there. So that's harder than transmitting classical information. And as a result, you can only achieve a lower rate, but you can achieve non-zero rates, and that gives you something called the private classical capacity of the channel. And there are random coding theorems for that, too. Finally, and the random coding theorem is given by now you just optimize over input ensembles for some v and some input distribution phi sub v, and you look at the difference of mutual informations. How much more information does this receiver have about the input variable than that one? And that tells you an achievable rate. You can do, again, random coding and something called privacy amplification to show it's achievable. And when you do this regularization, actually, you get the capacity. That's right. Yeah, and the reason that quantum key distribution actually works is that just by analyzing the input-output relations of these two guys, I can infer what this environment must be learning. Right? Classically, if I have some signal from A to B, it doesn't tell me anything about what transmissions from A to E might look like. But if I have a quantum channel from A to B, by doing tomography on what the channel properties are, I can figure out what the mapping from A to E is. Basically because if I was leaking information about A down to E, that would cause decoherence in the channel from A to B. So, right, so this, okay, so the private information just tells you how good you can do a quantum key distribution. And finally, if you want to transmit quantum information, you take a quantum state over here on the left, you do some encoding into all of the, now this is a quantum state here, into all of the channels. Your receiver gets some decoder and hopefully can reproduce the original input state. Okay, and this characterizes the sort of the optimal properties of quantum error correcting codes, and it tells you how you can protect quantum states from decoherence from noisy channels. And there's a quantity called the coherent information. Just it's given by the difference of the entropy of the output and the entropy of the environment, where you optimize now over all input to random or all input to mixed states. And this is, again, something you can show via random coding that is achievable. And furthermore, when you regularize it, it gives you the quantum capacity. So remember, it has to be achievable, and it has to be that nothing else can beat it. Right? So random coding makes it lets you show something's achievable usually, and then you have to use some inequalities about entropies to show nothing can beat it. Okay, so that's the crash course in classical information theory and a little discussion of quantum. And tomorrow we'll talk about bosonic quantum states and channels. And with that, I'll let you have a break.
Breakfast tea will be served in front of the auditorium. That is where this is.